This can take any shape possible. It could be a circular array. It could be just half a parabola would be a trajectory, and they mount antennas every so often on that. It can look like anything. But the classical way to look at arrays are called linearly spaced antennas with a constant phase shift, assuming the same magnitude current. Here's what I mean by this. Suppose they are all short dipoles. We're going to have a whole bunch of short dipoles. Doesn't matter how many. And we're going to say they're all spaced by a certain distance d away. And all of them have a current I naught. This one has a current I naught, but it has a phase shift alpha. This has a current I naught e to the j alpha, e to the j 2 alpha. And this one will have a current, and that current will be I naught, same magnitude, e to the j 3 alpha. And what they really want to know is the electric field pattern, the power pattern, and the electric fields from that. So they want to figure out the effect of stacking these things in some orderly pattern on the far fields. You're going to see it has an incredible effect on the overall gain of the system. But the way we do this is we can say, if we want to know the entire pattern of the array and the dipole, you start with the pattern of just the element, assuming they're all the same elements. So the pattern for this obviously looks like this. If you have a short dipole antenna, and this is the horizontal axis, you know you basically get a figure-8 pattern, right? Now I'm talking about the gain, or the directivity. And this would be proportional to the sine squared of the angle theta. Now when we take a look at the array itself, the array will have a pattern, and it depends on the phase shift, and it depends on the spacing. If we assume there's no phase shift at all, the array always has a maximum directivity in the broad side. So it will always have something like this, and it's dependent on the number of elements. Does that make sense to everybody? Remember, each one of these going to have the same current. If we assume there's no phase shift, we'll assume for this one alpha is 0. Now there will also be things called side lobes. So there'll be side lobe levels, and I'm just trying to show you, give you an idea. This would be the gain pattern of just the element. This is the gain pattern of the array. You with me, class? To get the total pattern, you take this times that. So when I take this and I multiply it by that pattern, the result is, well, you can see the main beam gets killed. And you basically get something, you can't tell until you do the work on this one, but it gets something where you're going to have like some kind of a, basically like this. Can y'all imagine that? And I'm just trying to give you an idea of what we're doing. So we need to find out what's called the effect of the array, or the array pattern. Now, that's the focus. We're going to assume isotropic elements. So now we go to the actual problem I start with. We care about the arrays. We're just focusing on the actual array pattern. Here's how it works. We're going to assume we're having an array, and it's going to be on this axis. This is called axis of the array. And we're going to start by saying we have an isotropic dipole with a current I naught here. And I'm not going to put a whole bunch of them. And then let me do it this way. Got one there. So we're going to have I naught here. And then we're going to have a separation distance d. Separation distance will be the same on all of these. This is going to have a current I naught. This is a current I naught e to the j alpha. This is going to be I naught e to the j 2 alpha. I naught e to the j 3 alpha. And you can see that this is really going to be I naught e to the j, and it's going to be n minus 1 alpha, where this is the nth element. I'm just showing you a whole bunch of currents stacked like this. It's in this book.
473, equation 8.99.
Now the next thing we do is we're going to assume we're in the far field. We're a long way. Matter of fact, we're going to assume we're at a distance r, where R is much, much greater than the number of elements times D. Think of this as we're looking at a star. That's how far away. So we're a distance R away, and at this point, we want the electric field. All right, I'll call this E, just E0, and this will be the field from any elements, the form of any field from the element. And the way it's normally done is they just say it's equal to K, and it's going to be times I naught here, and it's going to be divided by R, and then there will be a phase, E to the, it'll be minus J beta R. You'll notice there's no angular function here. It's only a magnitude thing, magnitude of current, and it has to do, I might as well put the phase of the current there too, because it will enter in. So I can put this as, it's an arbitrary constant K. K, and I can put down I naught E to the J alpha. Here's the first one. Now, the next one over here, we're going to assume again that these things are a long way away, they're in parallel. So the distance difference, if you look at this, and I better do something too. Dr. Wentworth's book, he calls the angle that the radius vector makes with the axis of the array phi. And that is important. That is not phi that is measured in the xy plane necessarily. It's the axis, it's measured from the axis of the array. And this is a linear array, so they're all, they're right on the axis of the array. So draw a straight line, that's where all the antenna centers are. Now, this distance here compared to this distance, call this R. If we call this R naught, this would be R1. This distance right here, delta R, is simply going to be equal to the spacing D, if you look at this, and it's going to be that times the cosine of phi. Now, just take a look at this. What I'm trying to show you is this difference in the distance. Remember, this ray is going out to a star, you might say. This one's going to the same star. They're absolutely parallel. Therefore, the distance difference would be right here. It's going to be simply D, the spacing, times cosine of phi, right? If I blow that up, sometimes you can't see it. But if you think about this as a right triangle, right? This is what I want, right? This is a right triangle here. That's this part. This is D, and this is phi. This is the hypotenuse right here, and I want the projection of the hypotenuse on this axis, so this would be D cosine of phi. And here's your check on this. What would the distance difference be if phi is 0? D. Well, if phi is 0, it's D cosine of 0 is 1. I mean, cosine of 0 is 1, it's D. What about if it's broadside? I mean, cosine of 90 is 0, right? Yeah, that makes sense. Okay, now I'm going to say, well, that means this field here would have the same formula. This I'll just call this E1, then I'm going to write the recursive relationship down. Would be equal to K, I naught. There would be that possible phase, E to the J alpha, right? The first one, E0, I mean, this one would be, let me make this phase 0 right here. That way it'll be easier. And make this one alpha. And then it's going to be E to probably a weather alert, a heat warning or something like that. I've been getting those left and right. I call this one R0. Let me call this R0. And this would be R1. This would be R1. Sorry. When I look at R1, it would be R0 minus D cosine of phi. This distance here, same as this distance, only I have to subtract off the D cosine of phi. With me? Now, if I look at this, 1 over R1 is about equal to 1 over R0. In magnitude, the D cosine phi is insignificant because R is so far away. However, that beta term is the thing that gets you, because that term is a phase, and the wavelength becomes a factor. So when I look at E1 here, would be equal to K I naught. Here it would be E to the J alpha over, and I can call that R naught, because R1 and naught and all the 1 over r terms of the same magnitude, then I'd have e to the minus j, and it would be beta times r naught minus d cosine of phi. I'm going to expand that. That means E1 itself is equal to some k I naught here, e to the j alpha over r naught, or r, and then I'm going to get e to the minus j beta, and it's going to be r naught, but it'll be times e to the plus j beta d cosine of phi.
Why don't you add anything to the bottom one?
Well, if you look at this, if I say R1 is, this is R naught, is going to be R naught minus d cosine of phi, right? We're assuming R naught is so much greater than d cosine. No benefit. You're so far away. Think about this. If you have 100,000, right?
Right.
100,000 minus 1 is the second one. 1 over 100,000 is about the same thing as 1 over 100,000 minus 1. That's a magnitude relationship. The beta, it has phase involved. That's a big difference. So when you break this out, you get this. With me? Now this is important. And I'm going to simplify things. I'm going to create a symbol that you're going to see appear over and over again. And then you'll start seeing where we're going. So for this, I can first of all say I'm going to introduce a function called psi. And that's simply equal to beta d cosine of phi. And after that, I can say, if I look up here at the next one, and I look at the E field from this one, if that was E1, E2 here, it would be equal to, it would still have the k, right? I naught, but now the phase angle would be e to the j2 alpha, right? It still would have 1 over r naught here, same magnitude. And then we're going to have e to the minus j beta times r naught, but it would be e to the minus j beta, and then it would be 2 beta d cosine of phi, wouldn't it? Because now if you look here, the path difference right here compared to the actual distance there is going to be, it's really going to be simply 2d cosine. So that would be E2. Now, if we go ahead and we want to say, what would it be for all of them? What we can say is this, and I'll put it here. I can say E total at a distance. You'll notice I didn't even put a polarity. It doesn't matter. The polarity itself doesn't matter. The real polarity is determined by the element, not by the array. It depends on the current's direction in the element. If it's a short dipole, half-wave dipole, loop antenna, that determines the polarity. So the total electric field, first I take all the constants out of it. I'm going to take the K, I'm going to take the I naught, I'm going to take R naught, I'm going to take e to the minus j beta r naught out in front. So what I'm trying to do is strip out all the constants that will be present in every single term I write. Then after that, well, now I look, the first term was this right here, right? So that's just 1. And then it's going to be plus, and here the second term is going to have this in it. It will be e to the j, and here it's going to be, I should write this down. I'm going to augment this if you don't mind. There would be, what I can do is take this alpha term and put it in here. Forgive me for doing this by the fly, and I can just say plus alpha here. And so beta d, instead of psi here, it would be beta d cosine phi plus alpha. Just take a moment. I'm trying to collapse this thing and get a constant that would just be repetitive. And the next thing I'm going to do is show you how when we index these numbers, what will happen. So this is E1. Here, this is going to be 1 plus And this is psi, so it's going to be psi. The next term will be e to the j 2 psi plus e to the j 3 psi plus dot 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 plus. And the last term here is going to be e to the j, and it's going to be n minus 1 times psi. And that would be the total electric field from the array itself, an isotropic electric field. Can you follow at least the gist of it? Now I'm going to collapse this. Now we're going to get a closed form solution for this, not an infinite series. I mean, something that's useful. See this recursive relationship right here? I want to get that, reduce the form of it. If we have 1 plus, or this is 1 plus a squared plus dot 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 plus a to the n minus 1. And we're going to call that a function. It doesn't matter what you call it. I'll just call this f of a comma n. This is a function. Doesn't matter what it is. It can be real, it can be imaginary, it can be a combination. Doesn't matter. So if I take this series, and then I'm going to take a times f of a comma n, I'm going to multiply the thing by a, and I get a plus a squared plus a cubed plus dot 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 plus a to the n, where n has to do with the number of terms. Now if I subtract that, so if I take that series f of a comma n, and I take that, and I subtract a times f of a comma n, I get a, or really I should say, f of a comma n here times 1 minus a. Now do this, subtract this from that. You can see all these things will become negative. I'll just leave it alone. So I have 1 up here, but I have no 1 down here, right? So I'm left with 1. Now the next term I have up here is a, but I'm subtracting a from it, right? That goes away. Then I have a squared, but I'm subtracting an a squared with me. I have a to the n minus 1. I have an a to the n minus 1 here, but I don't have an a to the n. So there's going to be that minus a to the n. And that means that series actually is going to condense down to f of a comma n is equal to 1 minus a to the n over 1 minus a. But I look at what do I actually have here. My a is what? Isn't my a actually e to the j psi? That's the thing that keeps repeating with different higher powers, right? So what I need to know is if that's the case, then I can say that series, this entire series here, the 1 plus e to the j psi plus e to the j psi, and this would be times 2 plus e to the j psi times 3, or I should say cubed, plus da da da, plus e to the j psi n minus 1. This whole thing right here condenses down to 1 minus, and it's going to be e to the j psi, and this would be n, right? Divided by 1 minus e to the j psi. I'm just showing you this is a series. I'm just trying to condense this series down. This is a trick that will save you a lot in your senior level course, communications. So whenever you guys see something where I have 1 plus or minus e to the j psi, I always think, I want to get this down to a form I know, which is a trig function. So what I'll do is divide out the top. What I'm going to do is pull out this angle divided by 2. Just watch this. So I'm going to take out e to the j, and it's going to be n psi over 2. So when I take out e to the j n psi over 2, and there's 1 as the first thing, I have to have an e to the minus j n psi over 2 inside. The product of those two is 1. Isn't it? Minus e to the j n psi over 2 here. Downstairs, I'm going to take out e to the j simply psi over 2. And then I have e to the minus j psi over 2 minus e to the minus j psi over 2 plus j psi over 2. Go ahead and multiply. This times this is 1. This times this is e to the j psi. All right, and then I can take this upstairs. So now I'm focused on this, but I'm going to take these two things. When this comes upstairs, that's e to the minus j psi over 2, right? So the whole top coefficient will become e to the j, and it will be n minus 1 psi all over 2. That's what's up top. Then, if you look at this, just take a look at this function. What is Euler's identity for sine of theta anyway? E to the j theta, e to the j theta minus e to the minus j theta over 2j, isn't it? Cosine would be what? E to the j theta plus e to the minus j over 2, not j down. Now if you look at this, if I multiply both sides of this by 2j, I get this. I don't have quite that. I have minus that, don't I? So if you look at this, if I make that a minus, and that a plus, and replace theta with psi over 2, you can see that the bottom term here, I can see that for that function right there, I can get e to the j n minus 1 over 2 times psi. On top, it's going to be the sine of n psi over 2 divided by sine of psi over 2. And that is, I can call it the array factor as a function of psi for the array. Now I'm just going to do one thing. I'm going to erase all that and put that there. Here is something, the weight of the actual current strength. And this beta e to the minus j beta r naught is nothing more than a phase variable. And then I have that, so I have this times the quantity e to the j, this is going to be n minus 1 over 2 times psi. And then we have the sine of n psi over 2 over the sine of psi over 2. Now I'm going to tell you that sine of n psi over 2 divided by psi of psi over 2 is very, very close to a sinc function for large n. That's this right here. And if you think about it, if you wanted, now remember, this is going to be, it has to do with the effects of the array. It has nothing to do with the element used. When you actually look at the array factor, or the effects of the array on electric field, all these things here, this part you can get rid of. This is going to be part of the array itself. So you can just say this is the effect on the electric field. This is called the array factor for the electric field, or array factor, and you can put down E field. If you wanted the total E field from an array, if you knew the phase angle, knew the spacing, you would find the electric field just from a single element. And I'm going to give you an example so it'll make more sense. Suppose I had an array and they were made up of just short dipoles, spaced by a distance. It doesn't matter how many. Now the electric field from a short dipole is J, eta, beta, I naught, and then it's e to the minus j beta r all over r, and then it's going to be times the sine of the angle theta in the a theta direction. This is assuming the electric field, or the dipoles are on the z-axis. If I have an array, this would be the element. Here's the elements pattern. Now, if I have an array of, say, it doesn't matter how many of them, when I multiply it by the array factor, it's going to be multiplied by simply e to the, and it's up there, j of n minus 1 over 2 psi, and then the sine of n psi over 2 divided by the sine of psi over 2. Here's the electric field that you know will vary as sine theta. Here's the electric field's magnifying, or the magnifying power. A lot of that you don't see real clearly. All right, so far you got, remember psi itself is beta d cosine phi, so it depends on the phase angle, or the phase shift per element, and it depends on, to be honest with you, the number of elements. But here is where I'm going to just show you some other stuff. And this is in his book, and I want you to listen to this part, because the real thing that we care about is the magnifying effect of this on the overall gain. If you have the overall gain of an array and for a given element, then you can see the magnifying effect of the array, or how much better it is, or higher the gain is. So if we think about the power, remember if we talked about total power, but if I'm looking at the average power density, I know it's equal to 1/2 magnitude of the E field squared over eta naught if it's in the far field, and it would be in the AR direction. If you think about this, this is going to be 1/2, and here we can take E of the element here, magnitude squared over eta naught, and this that I'm putting here is the power density, PAV, for a single element. And we're going to multiply that by the magnifying power of this array. Now the phase I don't care about. So now I get this times, maybe I just should have it like this, times sine of n psi over 2 over the sine of psi over 2 squared. When I have E squared, I know that E itself is the element's electric field times the array factor. So when I square the element's electric field, or 1/2 eta naught, that is just the average power density of the element at a given range R. Then I have to square the other part. Now, this phase thing, it's the magnitude. That J term of n minus 1 over 2, forget it. You don't care, that's phase. Care about magnitude.
I was just looking at the book, and it was saying that F array is sine squared.
That's what I have there. But the thing is, I use a small, I call it the array. This AF is for the E field. It's the weight on the E field.
Okay, that's something different.
You got to square it to get the power, average power, right? This power is proportional to E squared. When you look at this, this is really important. I guess in Dr. Wentworth's book, he'll call this capital F array equal to sine of n psi over 2 over the sine of psi over 2. Take that whole thing and square it. Well, what does it look like is a good question. Now, if you remember this, do you all remember your friend's sinc function? Sinc of x. Now, there's two definitions. This is the one I'm going to use. It's going to be sine of x over x. Another one is sine of pi x over pi x. That's a sinc function they use if you want all the zeros, or whether that function is 0, to be spaced at 1, 2, 3, 4, 5. If you plot this sinc function, and just plot the magnitude of it, plot the magnitude of sinc of x here, just magnitude. It does this. Starts at 1, goes to 0, and the 0 would be at pi, right? Then it would go up, and this would be 2 pi, down 3 pi. Here it would be symmetric, minus pi, minus 2 pi, and so forth. It looks like this. If you square it, it's more enhanced, right? It just does this. Basically like this. And when you square it, the difference here is about 13.2 dB difference, if you actually put this in dB. It's a number you're going to see over and over again too. If you have this function, if I have sinc of nx over x, and I square it. All right, I'll take this one. So if I have call this sinc of nx, Then take the magnitude of sinc of nx. Now the height of this is n. So instead of being 1, the height is n. If you square this function, the height is n squared. That means over here, this f ray here has a maximum of n squared. If you plot this function, it will have a value of n squared, the peak value, which means when I look over here, remember this antenna right here, that's really the average power density times the gain of the elemental antenna. I mean, take an isotropic antenna, find the power density, then multiply it by the gain of the element, and you have the value of the electric field. For the maximum value, it would be the maximum value of gain. Now, if you multiply it by the maximum value of the array, you see the gain goes up by n squared. So let me give you a specific idea. Suppose I have an array, and just say I have 4 of them. So I have 4 dipoles, 4 short dipoles. All right, here n is 4. If I wanted to know the maximum gain in the general formula for gain, first the gain max for this of the array and the element, max, would be the maximum gain of what's the gain of a short dipole? 3/2. This would be the max. Times what would be the gain of that array? 4 elements. Maximum gain.
4 squared,
Which is?
16.
So the gain goes up by a factor of 16. That's a lot. What would it be in dB? Call it G max, but I want it in dB. 10 times the log, that's a base 10 log, of 3 times 16 is 48 over 2, right? 24. So what's 10 times the log of 24? So 13.8 dB. Now, do you know what the gain of in dB of a, or better yet, short dipole? The gain of a short dipole is 3, right? What's the gain of a short dipole in dB? It's 10 times the log of 3/2. 1.76 dB. We increased that by over 10 dB with 4 elements. That's a lot. I'm just saying it's not insignificant. The power of magnification and maximum gain using an array is astonishing. As a matter of fact, you know what like deep space astrophysics or astronomy is, right? Remember, the receiving pattern is the same thing as the transmitting pattern. So when they're trying to gain information from very, very distant stars or galaxies, I mean, they're so far away, it's unimaginable. I'll send you guys, if somebody sends me, remind me if you can, I'll send you something about the span of just our solar system. It'll give you an idea, just the solar system. The scale of distances between us and the nearest star is just about unfathomable. I mean, it really is. It's like, so far, but the reason they can listen, and I mean, with these telescope, or it's really astrophysics that use this. They'll have large arrays, 100 dish antennas, and each dish antenna may have a single gain of 80 dB. That's 10 to the 8th. Think about this. 10 to the 8th, and they may have an array of 100 of these. So there's that times 10 to the 4th. It's 120, 130 dB a gain, and that means they can look and they can point it very accurately at a distant star, and they actually can account for the turning of the Earth and stuff. They can literally keep that thing right on target and gather light gather really microwave information over a period of time. And then they'll use, there's all these tricks for image processing, superposition and all that. Basically, they'll get rid of the noise to look at this. And the resolution. Has anybody ever seen these pictures of distant star systems? How do they get that resolution? It is mind-boggling. I mean, and I'm talking about microwave pictures. The actual, even the visual images, the way they have to do is time-lapse photography and catch all that information. It's amazing what they can see. But the reason they can do it is they use array, not just one-dimensional, but two-dimensional array. They'll have a 10 by 10. And they'll get they'll get ridiculous gain and the ability do imaging. So understand that, that's very important. Now, something I didn't say, this array factor here, and this sign, you know, when we're looking at this, well, how do I know for a given, if psi is beta d cosine phi plus alpha, how do I know what that pattern's going to look like? In this course, you don't. I can show it to you a little later, and somebody may want to do that for their project. It's a great project to investigate the actual array pattern and how to predict the actual array patterns. But it would be something to do. I mean, you can think of things. I want to investigate what for instance, the beam width versus number of elements for pick at different types of antenna elements, and what is the maximum minimum beam width? Because here's the one thing, when you have an array of antennas like this, you're going to find the narrowest beam width is when the phase angle is 0, you're going to get it in this direction. That's what it'll look like, I mean, for the main beam. You'll have these side lobe things here. You basically have that. This will be the beam width. Now, as this thing starts scanning this way, this thing will start broadening. And I can't prove that right now, it's a little long, but it's just something to take a look at. It would be a great project to investigate the characteristics of arrays. On beam width, maximum gain change, the effect on maximum gain versus the actual phase angle phi, and it's probably all online anyway. Probably the best thing to do at this point is a simple example. Good question in the back of your mind. Are you going to ask us to sketch a pattern, an array pattern for the test? No. But now I think about it, maybe I better, else you won't be attentive. So it might be a basic one.
Given a pair of dipole antennas separated by lambda over 4
All right, so D is lambda over 4. Go ahead.
and driven in phase,
Okay. Now, what that means is these currents are both I naught and alpha is 0. Go ahead.
determine for theta equals pi over 2.
Okay, so I'm assuming these are on the z-axis. Is there any indication of this?
There is no indication.
All right, well, we're going to assume that. You have to know which way the dipoles are pointed. We're going to assume they're pointed up. All right,
The value,
and they assume
determine
what?
the values of phi at the nulls.
Wait, hold on. Go again. So we get these dipoles, and this is the angle theta, right? From the z-axis, right?
And it says that's pi over 2. Theta equals
All right, so what they're saying is, we're right here. We're basically in this plane, the xy plane. Call this x coming out of the board, this y. We are at theta equals 90 degrees, or we are in the xy plane. So what I'm going to do is look right down the z-axis. And here's x, and here's y. And now we have two antennas, and they're spaced. D is lambda over 4 apart. Now the reason I'm saying that, if you look at these dipoles, the actual field pattern varies in the theta plane. Varies as a function of this angle right here. In the phi plane itself, you could take this and just spin it around. It has no variation. If you look at the, if you got an antenna this way, and you're at 90 degrees, well, the electric field value, or the square of it, for a given distance r is the same. So when we're here, we're in the xy plane, and we want to know the pattern of these. Both have I naught, right? They will have, if there's no phase difference, they'll have the greatest value broadside. If this is the axis of the array, I know I'm going to have a maximum there. Matter of fact, if I look at this, and I'll call this he calls it f of the array. F of the array uses the symbol phi, and phi is measured from x this way. So this would be phi. So if I wanted to find f of phi here, you with me, class? This is going to be equal to sine of 2 times phi And if you look at this psi is equal to beta d cosine of phi plus alpha. Here alpha is 0, so if alpha is 0, this goes away. Now the next thing I do is take beta d, right? All right, phi is beta d. Well, what is beta? It's 2 pi over lambda, and d is lambda over 4, right? Times cosine of phi. You can see that the lambdas cancel, and I get psi equal to simply pi over 2 cosine of phi. So now I have pi over 2 cosine of phi over, and this is going to be sine of, and this would be pi over 4 cosine of phi. Because now, remember, on top, it's n psi, right, over 2. Well, n is going to be 2. 2 divided by 2 cancels. And then I have times psi. So it's pi over 2, this. And this one is just psi over 2. Well, that psi, you got to divide it by 2, I get 4. Then I got to square this. Let's just plot points. If phi equals 0, what's the cosine? That's this, right out this way, if this is phi. If phi is 0, what do we have? What's cosine of 0?
1.
What is 1 times pi over 2 is pi over 2, right? What is the sine of pi over 2?
1.
All right, downstairs, cosine of 0 is 1. I have the sine of pi over 4. Sine of 45 degrees is 1 over square root of 2, right? But that's squared, right? So it's going to be a factor of 2. That means out this way, if I was to draw this proportional, you got the answers. Here's x. I would have a value of 2 out here, and I'd have a value of 2 here. They're always symmetric. Here's the 2 antennas. The spacing is lambda over 4. It's 2 out here, right? Now, plot another point. Now plot it at phi equals 45 degrees. This is the way you do it. You plot 2 or 3 points. You could plot 30 degrees. Might as well plot. All right, so what is the cosine of 30 degrees? Square root of 3 over 2. Now I have pi, I have 90 degrees times 0.866. If you can just tell me that, would be great. I'm trying to get some points here. And I'll tell you what it's going to look like. Something like this. Matter of fact, it's going to look probably identical to this. Yeah, give me the total value of f of phi.
2.42.
Oh, this is 2, right? It's got to be less than that. Unless we mess that up. Wait a second. Hold it. You know what? It should be 4 out here. You're right. You know what? We didn't square that, did we? Can you just check the value of that at 0? So sine of pi over 2 is 1. No, that isn't 2. No, it's 4, isn't it? Could you check that for me?
That's square root 2 in the numerator.
But if you square that, you just get 2. Yeah, that's the maximum of this thing is going to be n squared. So I can take a derivative of this with respect to phi. That should be n squared. There are 2 elements. That should be 4. This is now a function of phi, not psi. He wants the pattern, right?
And the values of phi where the radiated power is maximum.
Well, it's phi is equal to 0 if it's measured with, if these things, are they on the x-axis or y-axis? I put them on the y. If they're on the x, it's different.
And so the solutions are when
Phi is 0, it should have a maximum.
the maximum occurs when phi equals pi over 2 and 3 pi over 2. The minimum occurs
They're
when
not
phi
measuring.
0 and phi.
They're not measuring phi from the array then. Gain should go up as n squared. There are 2 elements that should go up by 4. The magnitude is 4, that's right. The magnitude is the measurement x is at 90 degrees, or it is perpendicular to the axis of the array.